Hello everyone and welcome to an introduction to online games. My name is Lorenzo Aurea and I will be the one conducting this presentation. So today we're going to look through some of the basic elements of modern online games. We'll be starting with a very brief introduction just to show you who I am and what I have done in the past and why I'm talking to you today. We'll be talking about some of the base concepts of networking in games, some of the common solutions which are used in online games, and we'll be finishing with some useful resources which I hope will be helpful in your studies. So let's start with an introduction about myself. As I said, my name is Lorenzo Aurea. I've been working in the games industry for a long while, 14 years, maybe a few more if you want to count also the non-professional years. But I've had a strong focus on heavy online games, so massively multiplayer online RPGs, so MMORPGs. Maybe you're familiar with the genre, and with esport games, so games that use the online experience to have an incredibly high fidelity in player experience. I've shipped many online games, including some that you can see here on the list. You can find maybe some more if you go on LinkedIn. Pretty easy to find. Not very important. What's important currently, I work for Ubisoft, which is one of the largest game developers in the world. I am a lead architect there. My team works with basically any production that has online ambitions in the company. I would like to point out that my participation is a personal one, so nothing of what I say today is going to pertain particularly to Ubisoft, and you should not be taking any of my statements as something coming officially from Ubisoft, but only as my personal opinion. Okay. So without further ado, let's talk a little bit about how do online games work. So let's start with a definition. What is a game? A game is a piece of software, and it does have a formal definition. And this formal definition is this. It's a while true loop, so it's a permanent loop that runs forever. It has only two functions, conceptually, obviously. One is a process simulation, so you can imagine that you have a number of objects in a space, in a 3D space usually, and they have a state, and that state evolves in some way usually through player input, or maybe if it is an autonomous game on their own. And then there is the second function, which is a frame update. And what that one does is that it takes the current objects and changes their state to take into consideration the inputs that have been sent. Okay, and then of course the loop repeats itself. So we're in front of a simulation loop at the end of the day. So it's a simulated world, if you want, of objects that evolve over time. And this loop is updated every certain amount of milliseconds. And you know, this measurement is actually what yields the famous frames per second count that you can hear in many games. It is a very frequent term in the industry. This is what they are referring to. How fast does that loop run? So what is an online game? An online game, it's still a game, obviously. So the previous definition still applies, but we have to add another piece. An online game is a game where players can interact with each other in some way and can consume services through a network, right? It's a very small addition to our previous definition, but it does hide three major engineering problems. One is the interaction between players, which can be synchronous or asynchronous, and also the consumption of online services. All of these three things are incredibly complex, and I hope that today you will walk away having learned a little bit about how do we handle professionally these very complex parts of development. Okay? So let's just start getting a little bit more in depth about what are the types of interactions that players can have. In synchronous interaction, what happens is that a player is influencing the state of objects which are shared with other players. The interaction that he brings to the world needs to be near immediately replicated, this is the term that we use, to other players which belong to the same simulation. You can appreciate that the complexity of this is the speed at which this update needs to happen, because the frames last only a few milliseconds. That's why it's called synchronous interaction between players. And the complexity of this is using a technique called replication, as I was mentioning, to copy the state of an object that has been influenced by my input in such a way that it is replicated, it is copied to other players in my same game with fidelity and with the shortest amount of latency possible. So here you go. This is our challenge, speed. In a synchronous player interaction, what happens is that past actions change the state of the simulation that is run by another player in the present. So basically, what I am playing right now is influenced by something that has been done by someone else, or maybe even myself. It doesn't really change much, but in a more distant past. So yes, sure, even in the synchronous player interaction, we are always acting on data that comes from the past, but here the difference is the real-time constraint. In synchronous interaction, we're talking about milliseconds. In asynchronous interactions, we will be talking about minutes or even days if necessary. It is obviously easier than synchronous because time constraints are pretty hard and they are difficult to satisfy. So, if you don't have those, obviously the system is simpler to make. There are many techniques to do asynchronous. A common one is called simulation replay. Basically, you use the inputs and the actions done by a player in the past to change the game that is played by a different player, right? And the main challenge obviously is the storage. If you're saving the state of objects in the past, waiting for a player to use them, to consume them, to influence their game, obviously you need to store them somewhere. And that, of course, when you have potentially millions of players, is something that can make things very difficult. So finally, we have online services. They are distributed services that add features to the game. There is a million of them. They all do all different things, but there are some commonalities that you can find. So, friend lists, matchmaking, inventory systems, profiles, you name it. I am sure that if you play even a little bit, you're familiar with many of these concepts. There is an infinite way of building them. There is an infinite way of features you can build with them. But the main problem is making sure that they scale. If you have millions of players, you want to make sure that these services never collapse, right? So obviously the challenge is capacity, right? If you have millions of players, you have to put these services somewhere. And even, even if some of the systems out there claim that they are virtually limitless, virtually is the key word. They're not really truly limitless, are they? So let's look at some of the common solutions which are used in the industry to defeat some of the problems that we have seen so far. So let's just start from some of the most common choices in the industry. So most online games are truly online games when the interaction is synchronous, and usually there is some degree of consumption of online services. Asynchronous interaction is usually limited to either user-generated content. So for example, in my game, you can make a level, for example, and I can share this level with you, and you can play my level or beat my score kind of things. Now, I'm sure that you have played a coin-operated game. You want to beat the high score. That's a form of asynchronous interaction, right? Since we're talking about networking, socket connectivity is usually done through UDP. I hope you're familiar with the network protocols. And the reason why the resource consumption is lower, there is potentially less latency because there are less control packets which are sent, because datagrams tend to be smaller. It's less CPU intensive because there is no recombination, there is no reordering. And one thing that you will see when you start working professionally in games is that CPU cycles are very precious. So you don't really want to use them to do something that you don't really truly need. And if you really need some of the features of TCP, you can re-implement them at OZ7 at the application level. Okay, this is actually something that is done fairly often. And games, as a caveat, games that have longer connectivity requirements in terms of length of time, they instead try to side with TCP. Some other common choices, the interaction between players sometimes are peer-to-peer, so the players are connected to each other, but more often and preferably they should go through a dedicated server. It's a lot easier to control what happens in the game if you control the part that decides what happens. Obviously, it cannot be influenced by players because you control the server and players don't. And also, it's a great way to ensure fairness between players. It's very easy to cheat if the game does not have any kind of direct connectivity, server connectivity, right? So data persistence is usually done through a lot of different databases. SQL databases, I have to say, are a little bit in decline. They are usually relegated to truly relational data, but anything that can be indexed usually goes in document databases like Mongo, for example. Basically, you need to think about this. A player usually operates only on its own data set, and it is very easy to index a player by a globally unique ID. And that is a perfect index for a document-based database, right? So with that, you're able to use effectively technologies that leverage GUI. So we can bring all these pieces together. We have a bunch of players. We have some of them are connected maybe to a dedicated server that are playing to each other. Some are consuming online services, and some of these online services have a database backend for persisting data. Let's look a little bit deeper what each of these individual pieces do. So before we start looking at the components, I think that it should be clear at this point that everything is highly distributed. And that means that there is one strategy that you should be looking at, which is divide and conquer, or divide et impera, if you prefer the Latin expression. Some cultures use one, some cultures use the other, so it's up to you. But it is very, very important that you master this strategy because it allows you to create applications which are going to be able to serve millions of users. And the principles of this are split domains, which means that every single piece of the application should be independent from each other in terms of responsibility. For example, I'm making a game where I can invite my friends. There should be only one component that decides who are my friends. Other components can consume that list, but that list should be owned only by one. The other one is loose coupling. It's impossible to make components completely independent of each other, but they need to be loosely coupled. It means that if components need each other, they should survive the absence of one another, right? To some degree. And then single source of truth, which means when there is any kind of data, there has to be somewhere a component that absolutely decides which data is correct in case of a conflict. So let's start with the first component, which is the game client. The game client, obviously, it's a game in the software definition that we have already seen. It is always assumed to be compromised, which means that you cannot trust anything that is coming from the client because, the client is running on a player PC or console and it might have been altered to cheat. Correct error handling is important, paramountly important to a very good user experience. And it will very likely implement UDP to talk to other clients if it is really truly necessary. That's something that you maybe do not want to do, and obviously the game server if there is one. And you want to implement HTTPS preferably to talk to online services. Most online services are built as RESTful services, so they use HTTP to be consumed, HTTP or HTTPS obviously. There are some fancy ways of building them, like using things like GraphQL, for example, but usually they're just consumed through HTTP because they're simple REST services. So how do clients communicate? They communicate in two ways. One is the fully connected mesh. It's in parentheses because meshes are not always fully connected, but the idea is all clients are connected to each other except when it is not possible due to network restrictions or a network address translation traversals. When that happens, usually one of the nodes routes the information to the nodes which are unreachable. The number of connections grow quadratically in a really bad way, so you can very easily tell by the formula, but it doesn't scale very well. The more nodes you have, and it explodes very fast. It's a very volatile network because if it is just clients talking to each other, they can come and go as they please. There is no reliability and no guarantee in terms of how long they will stay alive. So it's going to be very unstable by nature. Nodes, in case of difficulty, can route through each other. A, B, and C. If A and B can talk to each other and B and C can talk to each other, B can route, but of course that's something that you need to code. It's not something that happens by magic. And it is of course exposed to player manipulation because if my client is going to do the communication, it can alter the network flow, it can influence the messages, it can basically do anything it wants to the application, right? There's obviously no need for a game server when you have a fully connected mesh or a mesh in general. So it's very cheap because you don't have to pay for it and you don't have to maintain a game server. You just have to maintain the game client. Many classic games are built this way. The way it's presented, it sounds like it's a bad idea, but there are cases where this is sufficient. But the other type is having a star network. Okay, in a star network, the clients connect only to the game server. Okay, so there is a dedicated game server that arbitrates everything. Obviously, you will have to pay for this game server to live somewhere. You need to develop this server, and also it makes things very complicated for your development team because now they have to debug 2 applications instead of 1. You need to maintain this game server, you need to patch it, you need to test it. Like the complexity explodes very quickly, but it brings strong resilience to cheating because now the simulation can be run on a node that is unreachable to players. And servers are also very reliable. They're not just resilient to cheating, they're reliable also because they're hosted in very stable locations. DDoS obviously is an issue if it's a distributed denial of service, but that is something that can be managed as well. And players do not connect to other players, so no malicious activity can happen. You can do it, obviously, by using a mesh, but I certainly do not recommend it. It's usually a poor idea. So speaking of the game server, it runs a similar code as the client, and there are a few ways to make one. One is a bottom-up approach where you build one from scratch using the same code libraries that you use for the game client. And the other one is to do a headless client. So basically you take your client and you strip away as much as you can. Usually the rendering engine is the first to go, and that is a top-down approach. Okay, they usually run on Xnix, be it Linux, FreeBSD, whatever flavor you want, it doesn't matter. Because it's cheaper, pretty much. It's not like Windows or Linux are particularly bad or good. It's not a preference strictly based on performance. It's more about price. And Linux has certain features which make it very good as a server component, but I actually discourage very much about using any of the exotic features of very specific types of Linux, because in case you need to migrate, that might make your life very, very hard. There are 2 types of game servers. One is the thin server. The thin server is a small process, so very small footprint in memory, very lightweight, highly scalable because you can run many of them in parallel, very cheap to host because you won't need expensive hardware, very fast to start, and it's going to be very easy to test because it's fast to start, right? So basically, it's a great strategy when you want to move at the fastest speed possible and you want to have a very comfortable way of working. However, the drawback is that because it's so light, its ability to validate the gameplay, it's going to be very limited, right? So it's something that you're going to pay in terms of fidelity of your simulation, right? So very often what happens is that since checking very little actually doesn't bring much value, very often thin servers are only used for message routing between peers so that you avoid having a fully connected mesh. The other type of server, if one is thin, obviously is fat. It's a large process, so it consumes a lot of resources, be it CPU or memory. It's often comparable in weight to the game client. It's not guaranteed, but sometimes it is. And the scaling requires a lot of good architecture. So fat servers are a lot more difficult to do than thin ones. However, well, you can also fix the problem just by throwing money at it, but that's usually not very cost effective because they're expensive to host. These are large processes that require big hardware, but the advantage is that they can run the entire game simulation if you want. And that allows you to have a level of control and reliability that cannot usually be achieved with a server, right? So connected to these two types of servers, there is another type, which is the authority model for the server. The server needs to influence that simulation that we were talking about earlier, and can do it in two ways. Partial authority. In partial authority, some game systems require validation and some others do not, are left to the control of the clients. So basically, they're either shared with the client, like there is some part of something that is decided by the client, so there is some degree of client trust. So this violates the principle of never trusting the client that we established earlier. And the result is that the server code is a little bit less complex because the server doesn't have to check so much, right? So the systems that do not need any server validation obviously are very simple to write. And the result is that actually you end up with code that is very hard to read, because some of your code will go through server validation, some other parts of the code are not going to go through server validation, and maybe some systems are just going to be half and half, with certain parts validated, some other parts which are not validated. And if that is the case, well, it's going to be difficult to debug what's going on. It's going to be difficult to add more features because it's becoming increasingly complex to make the determination in your code about what should be validated and what shouldn't. So this is a fast choice in the beginning, but it has a mounting cost over time. The opposite is full authority. In full authority, all game systems require validation from the game server, and basically that's it. As a partial exception, there are a few tiny things which are left in the hands of the clients. For example, your player position, or better said, the input on your player position is usually, for efficiency reason, left in the control of the client. But there is a strong validation in regards to movement being legitimate, so that you cannot just teleport around any way you want. So in full authority, you need to check everything. So more server code is required, obviously. More client code is required because every single system will need to acknowledge, will need to receive an acknowledgement from the server. But in exchange, you get a very unified way of building all systems. You need to validate everything that you do. Full stop. No exceptions. As a whole, you have to write more code, but it's a lot simpler to understand because it all uses the same pattern. And yes, here we have a higher upfront cost, but the cost of maintenance, which is a repeated cost, is going to be more constant over time, and it's going to be fairly low if you work well. Okay, again, there is not really like a strong automatic good answer. These are just different ways of doing things. Okay. So we were talking earlier about the complexity of sharing state in a synchronous way with other players. So let's spend a few words on replication. So replication is a technique to share object state between peers. And the peers could be anything. Could be clients. It could be servers. Okay. Basically, all these peers, they belong to the same simulation and they need to see the same state of the world. How do we do that? Basically, every peer ends up receiving an update that comes from the past, and it needs to apply that past to its current present. You can imagine that even if the concept is simple, the complexity is very, very high. There are many techniques to mask this latency, this delay, this fact that we're applying information from the past. There are a few. There is something for trajectories, which is called dead reckoning. It's a technique that actually comes from the military navigation, actually. Now you need to imagine that there are two ships. moving on the ocean and one is trying to fire at each other, you need to make sure that your cannons are aligned not where the ship currently is, but where the ship is gonna be when the cannon shot is actually going to hit. It's a relatively complex technique. I have some links in useful resources in case you're interested. But there's another thing which is called preview and rollback for actions. Basically, you do not want to create a game where you do an action, that the action actually causes a verification on the server side, and then the server side decides that the action wasn't correct and it gets rejected. This happens very rarely, actually. So what you do is that you execute actions immediately on the client side as if they had the immediate execution that you would expect from a single player game, and in the rare case that they need to be cancelled, the action is rolled back to have no effect. And then there are many others. These are all part of things called client-side prediction. It's a series of techniques which are used to basically interact with the objects in your system with data coming from the past. And bottom line, doing this well or doing it badly makes the entire difference in terms of quality of the game. So core concepts and replication, this is a huge world. It would require a whole presentation on its own, so we're going to go very briefly on this. Every object in the simulation can be owned by the current peer. So in that case, it's a master object, or it can be a copy of an object that belongs to somebody else. So it's a replica. So there are some systems that have some exotic types. I've linked the documentation for the Unreal Engine, which, by the way, you can download for free if you want. That uses some exotic variations of this. We're not going to go into those, but it's just to say the replication is a very complex world. So typical replication loop, what does it do? It observes the state of all the objects that the current peer owns, chooses which part of the state to replicate in case it has changed. So it has two choices. Either you replicate the entire object, or you identify the changes and you replicate only those. And that's called delta replication, because you only replicate the differences. The important part here is that it depends on how much CPU costs you to do this. Again, CPU is precious. It might be better to replicate everything instead of spending time to identify when something has changed. Okay. Then the changes are transmitted through the network, and then everybody who has a replica of the objects that have changed receive that state, apply it, and the loop. Okay, so this creates very clearly a constraint where replication is basically making your application a real-time application, right? Because every replica is updated with data that comes from the past. And if that past is too far back, that information is stale and I cannot do anything with it. Okay, so you can expect a delay of 50 to 250 milliseconds in your state. It can vary depending on the application and the infrastructure. Maybe more commonly, you would say between 50 and 100, but it depends on the type of game that you're making, and the tolerance of that time depends on the game that you're making. And also, we have another issue. How do we establish when we have a single source of truth? What happens if I start getting data that is conflicting? Now, I mean, right now we've only been reasoning in terms of single objects, but what happens if we get multiple updates from objects from different peers and the resulting state of the world is something that is incoherent, that violates the game's the rules of the game? What do you do? Well, you need to have a single source of truth. Something needs to tell us what is the truth state of the world. So obviously, if you have a game server, that's the truth, end of story. But if you don't have it, you have a problem. What do? You don't have a single source of truth. You have a number of peers, but they all have different opinions. So what do? You vote. So this is going to be like a very brief parenthesis on a thing called consensus networks. These are networks which are used when you don't have a single source of truth. So what happens is that every peer will be able to vote on the state of an object. You do not want to trigger voting all the time because it's an expensive operation, but it is a technique that is used. And the fact that you have very unstable networks, particularly in the mesh world, as we saw earlier, what happens is that every object might end up having a slightly different state at a given time. So how do you reconcile when all these states conflict with each other, or when an action has different outcomes? You have peers vote on a result. If a result is conflicting with the rest of the results, you have to either accept or discard it. And if you accept it, then you have to apply whichever rules you want to apply to fix the conflict. It's a huge topic. There are many voting strategies, many consensus techniques. Some of them are majority vote. So the peers just vote, accept, reject, and whatever wins, wins. You can have a qualified majority where the most voted outcome wins, but if it was my data that caused a conflict, I do not vote. And another way is the weighted majority, where all the votes have a weight, and this weight depends on usually who is favoring themselves. Basically, if I am voting for myself for something that advantages me, then my vote is less important. It values less, is worth less than the vote of someone that is voting against his own interest. Okay, again, there are many techniques, but it's just to expose to you that there are ways of working without a game server. They're very complex, probably not recommended unless you're very good at what you're doing, but they're nonetheless a possibility. And then we haven't even talked about online services, right? So it's a huge universe of possibilities. There are many commercial solutions out there. I've quoted some. You can find them on the public internet. You can look them up. You will see that they're all very similar to each other, actually, because basically the online services out there, they all tend to do the same things, because at this point, player expectation is very well solidified, right? They're mostly, if not all, cloud-based. I'm not sure if Nakama is. Maybe it's not. I don't remember. But to be honest, at this point, you can expect that all of these services have some kind of cloud backend, so that they're geo-distributed and they're scalable. They're usually consumed through HTTPS because they're RESTful, and they have one important challenge that is common to them all, which is scalability, right? In the world of today, you can have a game that has millions and millions of players, preferably all at the same time, right? So they can all enjoy with each other. But this clearly, from an engineering point of view, creates a substantial challenge. How do you conquer it? Well, scale is what makes the difference between a system that works well and one that gets abandoned and forgotten. And again, we go back to the strategy that we have talked about in the beginning. Divide and conquer is the way to go. It has become pretty much the default way of working. So you split domains between services. So every single service is fully independent in terms of responsibility from each other. Again, they can talk. It's not forbidden for services to consume each other. That's okay, but it needs to not be a dependency, and there needs to not be a responsibility that is split between services. You want to have stateless services. That means services which run on application nodes but do not own any data. So if that application node dies or crashes or it's compromised or it loses access to the internet, it doesn't matter. Some other node can pick up where the previous one is left. And then you want to apply the principle of locality, which says that all the nodes that are going to be consumed by a user are going to be relatively near, often in geographical terms, to where the user is located. And the people that he is going to interact with are going to follow the same principle. Just to make a simple example, let's say that I am in France and I'm playing with some friends in France. That is a great example of principle of locality. We will all be connecting to nodes which are located in France, maybe all the same node even, and it is extremely unlikely that we will need to access information or services or data which comes from other parts of the world. Okay, this is a very, very important principle. And then, because as a consequence of the principle of locality, the data strategy that you want to employ, it's called eventual consistency. If my friends, to go back to my previous example, all play together with me, we need to have the data persisted in in France somewhere or in Europe somewhere, so that it can be easily reached there. But let's say, for example, that one of us goes on vacation and we are in Australia, for example, and we still want to play online because, like we love playing online so much. And in that case, my data in Australia needs to come all the way from France. In an eventual consistent strategy, what happens is that the data that doesn't follow the principle of locality gets slowly, that's why it's eventually consistent, written across the entire database installation across the world so that the data can be accessed anywhere it needs to be. Okay, so just a word on databases. Statelessness obviously requires you saving your state somewhere because you need to separate it from the logic. So you will need to persist it, and to persist it, you will need a DB somewhere, right? So data that is relational will definitely go in a SQL database. SQL databases, they were made for data that is relational in nature, and they should be used as such. Big suggestion: do not use databases for structures that were not made for. It's not smart. There are alternatives today. Okay, so speaking of SQL, you want to use relational data. You can scale it. It's complicated, but it's well understood. There are many techniques, and all of the providers out there provide you ways of scaling your SQL database. There are some common technologies that literally everybody is using. There is PostgreSQL, there is MySQL. These are all technologies that you can find for free. So if you want to play with them, you can. And the other type of data that we use, usually it's in document databases. As I was saying earlier, very often players act only on their own data, and that is data that can be very easily indexed by a globally unique identifier that is assigned to a player. Okay, so many of these document-based databases, they scale very well, and they're originally made for this. Some common ones are like MongoDB and Redis. Again, you can use these for free if you want, so you can look them up, you can play with them, no problem at all. They have community editions which are completely free for even for application purposes. So if you want to build something, you totally can. And then of course there are special purpose databases. There is many of them. We're not going into them today, but you have things like Cassandra, InfluxDB, and honestly countless others. The bottom line is databases will be needed to persist your state. Use the database that best fits the structures that you're building. Okay. Finally, microservices are a relatively new trend. I mean, it's not that new, but let's say that it's the latest in terms of creating services. It follows the Google way of doing things, which basically means chunking up everything to the tiniest amount possible. It's very difficult to define because there is no formal definition, because people cannot agree on what qualifies as a microservices. So we could probably regard it more as a philosophy than anything. But the principles are basically take divide and conquer and bring it to its extreme consequences, right? So you want to have full independence between each individual service node, so you can all make them act independently from each other. Even nodes that serve the same application, okay? You want to have independence everywhere. You want to have them stateless. Yes, you can have them stateful if you really truly want, but you really shouldn't. And all parts of the application can be individually manipulated, changed, updated without any kind of disruption to the larger application. Okay, so basically we're really pulverizing the application to such a fine level that we can act with a very high degree of precision. Okay, and scaling, if you just want to have something that holds more users, since everything is so pulverized, we can just spin up new application nodes, new service nodes, and we're done. And that's the scaling in microservices. Okay, the most common platform for Kubernetes for microservices is called Kubernetes. It's also known as K8s or K8s, as you might see it in literature. It's an open source project, but mostly it's Google contributing to it. It's very complex to learn, so we're not going to talk about it a lot today, but it's just to mention it. It has these strange attitude of calling common things in the rest of the world with its own very specific names. So in the beginning, I think the learning curve is a little bit steep because you have to relearn certain concepts, or at least you need to learn the Kubernetes version of them. So the learning curve is not going to be great, but it attempts to solve the orchestration problems caused by going with the microservices philosophy. Because if you have pulverized everything so much, an application can have thousands of nodes. You need to have a way of orchestrating them all. You need to have a way of spinning them up, shutting them down, updating them. Like if everything can be touched independently, you really need something that allows you to do it in a way that is easy. And Kubernetes facilitates that. It is based on containerization. The de facto standard is Docker. That's another free technology if you want, just as Kubernetes, by the way. So if you want to play with Docker, I definitely recommend to look into it. It's a very useful skill in the professional world today. So certainly something that will make you desirable on the job market. And I certainly recommend you look into it. Okay. So wrapping this up, we have literally just barely scratched the surface. We have been incredibly superficial. Online games are built with a huge variety of technologies, concepts, and we had time today only to just give you a glimpse of how huge this engineering world is. But practice will make you learn everything that you need just by doing. So my encouragement is, if you're interested in making games, make one. It doesn't have to be a good game. It just needs to work so that you can apply your engineering concepts and do something that is a fruit of good engineering. And if you want to start from somewhere, make an online version of tic-tac-toe. It's a way of practicing everything that we have learned today. Online development will make you face a limitless amount of unknowns, and it will challenge you to find creative solutions which very often don't have a standard solution. So you will need to get very creative. But I hope that today some of these unknowns are going to be a little less unknown, right? So with this, my most sincere good luck, enjoy yourself, make games, and I hope to see you in the industry very soon. Okay? Thank you very much. Before we finish, we'll just go very briefly through the resources. I have some links on the dead reckoning and client-side prediction in case you're interested. On networking, I've quoted in particular is a networking in Halo at the Game Developer Conference 2011. That's an exceptionally technical but exceptionally interesting presentation of the techniques used in Halo, a very famous online shooter. Some references on online services. And finally, if you want to contact me, I'm going to give you my personal email. You're very welcome to drop me a line. You can contact me at lorenzo.aurea.it@gmail.com. Thank you very much for following this lesson, and again, good luck.